Hey everyone, today we're going to be going over the ratio test for the interval of convergence, or just the ratio test, because that's a lot easier to say. So, to get started, I'll write down the general formula of the ratio test, which is L. Oh, I'm using the wrong brush. Okay, let me change that. So, L is equal to the limit as n approaches infinity of, that's like a diagonal 8. Hold on. Infinity of the absolute value of a n plus 1 over a n. Round that out. So essentially what this is doing is, when you have an infinite series that you're not sure whether it converges or diverges, you can use this test to, see if it converges or diverges. And the reason it's called the ratio test is you're comparing the nth term of the sequence to the term after that, the n plus 1 term, so just the term after n. In looking at the ratio, we can determine whether or not it converges. So let's go over the conditions for that. So if L is equal to, let's say L equals 1, this means that we have we can't really say anything. So it's more testing required. It's inconclusive rather. So I'm not spelling out inconclusive. I'm going to spell it out. Never mind. So it's inconclusive. You would have to, did I spell that right? I don't care. It's inconclusive if L, or our limit, gets 1. It's just, we'd have to use a different test. This doesn't tell us anything. If L is less, or, well, alright. If L is less than 1, this means it converges. I forgot the end. Converges. And lastly, if L is greater than 1, it diverges. So now that we know the different conditions for convergence, divergence, and needing to use a different test, let's go over an actual example. Or, well, I'll be going over 3. So the first one we can go over is just the harmonic series. So we have the sum as n goes from 1 to infinity of just 1 over n. Now, the way we would approach this problem is, we already know that the harmonic series diverges, but I want to show that with the ratio test. So the way we'd approach this is we would set this to be the limit. And usually you'd have absolute value bars, but since this is the harmonic series, we're not going to go into negative values. So instead, we don't really have to, but I will just in case. Limit as n goes to infinity of, so what we do is, for every n, we're looking at the term after that. So it's just n plus 1. So we would have 1 over n plus 1, and now we multiply by the reciprocal of the original function. So in that case, 1 over n's reciprocal is just n over 1. And now this is where we do some cancellations. So we would just have n over n plus 1. So this gets us our limit as n approaches infinity of n over n plus 1. And we don't need absolute value bars. So in this case, we see that the n's, we have n over n. We can cancel these out. N over n, and what we're left with is just 1. Now, since this is, as stated previously, if L equals 1, then the test is inconclusive. And we know the harmonic series diverges, but every time we get L equaling 1 doesn't necessarily mean that this is always going to be a divergent sequence, which is where I'll show a series that converges, but our limit also equals 1. I didn't need to delete that whole thing, whatever. Okay. This time we're going to be looking at the Basel problem. So we have the same thing, but it's just squared. So it's sum as n goes from 1 to infinity of 1 over n squared. And in this case, we do something slightly different. n approaches infinity of 1 over n plus 1 squared, that's a horrendous 2, squared, multiplied again by the reciprocal of our original function, so it's just n squared over 1. Now, we would get the limit as n approaches infinity. That's like half infinity, that's just 0. Infinity of n squared over n plus 1 squared. Now, usually, this might look a little scary, but because we're dealing with a polynomial here, when we expand out n plus 1 squared, the highest degree polynomial always takes precedence, and in this case, the first term is just n squared, so they just cancel out. Once again, we're left with 1. And in this case, we know that the Basel problem converges, so that's 2 examples of when L equaling 1 can have it either diverge or converge. Now, I don't have an example for L just being greater than 1 and diverging, but I do have one for when L is less than 1 and converges. So let's look at that. So once again, we would have our sum, so n goes from 1 to ooh, we saved it. Alright, nice. Infinity of n to the 10th, so n raised to the 10th power, over 10 to the nth, so 10 being raised to the nth power. Now in this case, we're going to have to do what we did earlier. So we get our limit as n approaches infinity of the absolute value, this time we'll use absolute value, of, once again, n plus 1, so replace every n with n plus 1, raising it to the 10th power, over 10 to the n plus 1. Now we're going to multiply, I don't know why I made the dot bigger, whatever, by the reciprocal of the original one, so we would have 10 to the n over n to the 10th. Now, these, what happens is, the n and n plus 1 cancel out, and what we're left with, oh, the 10 also cancels out, is 1 over 10, or just a 10 on the denominator. The reason for that is we're having n minus n plus 1, so we get a negative exponent, which in that case, instead of 10 to the negative first would be 1 over 10. So now what we're left with, and in this case I'm gonna, not an equal sign, in this case I'm gonna split up the fraction 1 over 10 with the rest of the thing, so we would have our limit as n approaches infinity of 1 over 10 times n to the, or rather n plus 1 to the 10th over n to the 10th. And as I explained earlier, because even though this might look a little scary and we have, n plus 1 to the 10th, this is a really near, I wouldn't say impossible, but incredibly annoying binomial to expand out. But we know that the first term would just be n to the 10th, and higher degree polynomials take precedence, so the n's just cancel out, and also the 10. And what we're left with is just 1 times 1 over 10, which is just 1 over 10, which of course is in fact less than 1, so this converges via the ratio test. Converges via ratio test. So we've looked at 3 examples. I don't have one for divergence, but you could probably figure one out. Just have a series where n, or rather L, becomes greater than 1 and it diverges. Yeah, that's about it. There's no zeta function video this week, because I never figured it out. I'm too stupid for that one, so maybe next time, but for now, we're not doing that. Instead, you get a ratio test video. So yeah, with that being said, thank you for watching.